Good morning, amazing physics students. This is Mrs. Armbruster. I am sick and cannot come to school today. So we're going to work through an abbreviated version of the notes that we were going to cover today as a class. When I'm back on Thursday, we'll go through some of those activities. We'll do a couple of these things again. So if something feels confusing, what I would really like is if you star your notes, find the spot in the PowerPoint, and just come to class with as many questions as you can on Thursday, and we'll get you straightened out. But for today's class, we're going to talk about the concept of motion at a constant velocity. I think for a lot of you, if you came from physical science, you've probably talked about a lot of these concepts before. And on Thursday, we're going to build on this and talk about constant acceleration. But I think it's going to be an okay thing for you to watch and just bring all of your questions that you've got on Thursday. I'll be ready to answer them. So when we're describing motion, I have a few vocabulary words that I want to make sure we're all on the same page for today. So we have 3 words that can describe where something's located, and those words are position, distance, and displacement. Whenever we're talking about location, the units for that are always meters. And we'll talk about that a little bit more on the next slide. Then we have 2 words that can talk about how fast you're moving, and those 2 words are speed and velocity. In this class, the units for those are meters per second. We're also going to group all of these words, and I have a clip from Despicable Me that I promised to show you on Thursday, into the categories of vectors and scalars. So a vector is any quantity that has an amount. The science word for amount is magnitude, but we don't have to panic by that. It just means amount and direction. The direction is sometimes really intuitive. Sometimes it's a little bit different, but it can be things like north or south or positive or negative or left or right, up or down. And a scalar is any term that just has a magnitude, only an amount, no direction. So there won't be a plus or a minus with any of those terms. They'll always be positive. So if we ever see a term that I'm going to tell you is a vector, we have to remember to include direction with it. And if I ever tell you that a term is a scalar, it means we just need an amount. We don't need a direction with that amount. The first pair of vectors and scalars is distance and displacement. So the word distance is a scalar. It tells you how much ground was covered. Displacement, on the other hand, is a vector. It tells you how your position changed or how your final position compares to your initial position. So here's an example problem. It said Callie walks 70 meters east and then 30 meters west. What's her distance and what is her displacement? Okay, so when I'm figuring out this, I'm going to draw myself a little compass. Never north, east, south, west. Okay, so Callie's walking 70 meters to the east. And then she's going to turn around and come back 30 meters to the west. The total distance that Callie walked was 70 meters plus 30 meters, or 100 meters. But her final displacement was only 40 meters east of where she started. So the total amount that she walked was 70 plus 30. But in the end, since she turned around and walked backwards, she ended up only 40 meters out of place, 70 minus 30. The next pair of vectors and scalars are speed. Here's one thing I love about this. Speed starts with the letter S and is a scalar. Velocity starts with the letter V and is a vector. Speed tells us how far an object travels in an amount of time, regardless of direction. You can think of it as distance traveled divided by time. Velocity, though, is how fast you're moving and the direction. A good way to think about that is displacement over time. Or if you want to see that with an equation, displacement, we represent displacement with the letter x. Let me make you a little note, sorry. Displacement. I would think of that as like x marks the spot. And time we represent with a t. Now, hopefully this kind of makes sense because remember we talked about speed is a meters per second, distance over time. Oh, I kind of got ahead of myself. For speed and velocity, both of them have the same unit. Now, here's something kind of interesting. If for any one trip, your speed and velocity are equal, usually they're not equal. Your speed and velocity are usually different. But if they are equal, if you think kind of carefully, you can figure out something special about the motion. I would think about that by thinking, okay, we have to compare my distance over time to my displacement over time. So if my speed and velocity are the same, that means distance over time equals displacement over time. Or my distance must equal my displacement. That's only true if you're traveling in one direction and never turned around. Otherwise, your speed, your distance and displacement, and therefore your speed and velocity are different. If you're traveling at a constant velocity, which is going to be our examples today, what velocity is the rate that your displacement changes over time, or the change in x, which is my positions, divided by the change in time. Here's our first of our equations for this unit. The f next, like after this, it's called a subscript. That stands for final. So my final position minus my initial position. Sometimes I see students who think that that means you have to square or that f and I are new variables. We're going to treat them as one variable, and we'll do an example in a second that I think will help that make some sense. But final position minus initial position over time will tell me my constant velocity. Okay, now let's look at some of these graphs. What would the constant velocity look like on a graph? Well, the first kind of graph that you might look at is a position and time graph. On these graphs, on the x-axis, you put time, and on the y-axis, you put position. That's true for all. We're always going to put time on our x, and then we'll put our other variable on the y. These are really cool because they give you a visual of where is an object in some amount of time. So I could say, okay, when my trip started, 4 seconds into the trip, I was at a position of 4 meters. And I could tell, okay, 6 seconds into the trip, I was at a position of 6 meters. So it can give me an idea of where I'm moving and how fast I'm doing that movement. Okay, here's 2 kinds of position and time graphs. And I want you to take a second before I tell you and think about what kind of motion is this showing. So the graph on the left is a position and time graph. And the position, it's a flat horizontal line. The position is never changing. This means that this motion, it's not moving, it's stopped. We could say it's not moving, it's stopped. You could also say that its velocity is 0. All of those things mean the same thing. On this graph on the right, though, it is moving. I can tell that because there's some slope to the line. Its position is changing as time goes on. In fact, I could describe that change by, I could give it a velocity. But for now, let's just say that it's moving. See how it's a constant? It's a line with a constant slope. So this would tell me that I'm moving with a constant, oh, sorry, I meant to change colors. I'm moving with a constant negative velocity. And we'll talk about how to find the value of that velocity in a little bit. Okay, here's 2 graphs. We want to identify things that are similar and things that are different. Well, both graphs are moving, they start with the same exact motion. They moved 2 meters forward in 2 seconds. After that, both graphs then stop moving. Here's where the change happens. On the left, this graph shows that the whatever object is making this motion goes back to its initial position. Where on the right, the object kept moving forward. So this object turned around the object on the right continued its motion. But at the end, I went back to doing the same thing. Both objects came to a stop, but they were just at different final positions. The one on the left returned to its initial position. The one on the right ended up 4 meters in front of where it started. I'm getting that by looking at the graph. Where the graph ends, what position am I at? Sorry for the highlighter yellow. This would have made more sense in class. But we can read position and time graphs to determine those two quantities we talked about earlier, distance and displacement. So here's a graph, and my questions for you are, what is the distance traveled by the object, and what's the displacement of the object? Okay, distance, this object started at 0, went up 3 meters, then it took a rest, then it came back down 2 meters, and then it stopped. So it walked forward 3, paused, backwards 2, and then stopped. The distance that was traveled was 5 meters. 3 meters plus 2 meters. The displacement, in this case, since they didn't give me more information, I would just say my final displacement was plus 1 meter. Another way you could come to that is to identify for displacement, identify the initial position and the final position. Well, my initial position is 0. My final position is 1. So my displacement was plus 1. For displacement, we don't care about the middle, only the initial and the final and how they compare. Next piece we're going to add to these graphs is how to find how fast you're moving, and that's from the slope. Remember, slope is something we've been reviewing in this class. It's rise over run, or change in y over change in x. And the slope of a position time graph tells me the velocity. So here's a graph that has 1, 2, 3, 4 different line segments, and we're going to find how fast it's moving in each segment. It's a good idea, I think I'm going to talk about this later, but it's a good idea to always double check, like this line, it's counting by ones. This is also counting by ones. So in the first section, for the first 2 seconds, from 0 to 2 seconds, this object is moving up 1 over 1, up 1 over 1. It's moving at 1 meter up every 1 second. You could leave it like that. I would probably simplify to 1 meter per second. Then in the next section, I'll highlight it. It stays at the position of 2 meters from 2 seconds to 5 seconds. It does not move. So from 2 to 5 seconds, I'm not moving. The way I show that is 0 meters per second. Next line segment, I'm coming back down now. I'm going down 1 over 1, down 1 over 1. So from 5 to 7 seconds, I'm traveling down 1 meter over every second. I would simplify that to -1 meter per second. In the first segment, it was climbing, so it had a positive velocity. In the in this next segment, it's falling, so it has a negative velocity. Then it ends, it's at 0 and it stays at 0. So from 7 seconds to the end, I'll call it 9. It's not moving again. It stayed at that location. Okay, here's an example of why it's important to pay attention to scale. Often you'll look at graphs where the x and y axes are counting by the same amount, but let's look at this graph kind of carefully. It starts at 0, 0. On the x-axis, I go 2, 4, 6, 8, 10. I'm counting by 2s. On the y-axis, I go 5, 10, 15, 20, 25. So a really common oops that I could see students do at the beginning of the year is this question: how fast is the object moving in the graph shown? A really common wrong answer is -1 meter per second. That's a wrong answer. What students are thinking is down 1 over 1, down 1 over 1. What's actually happening, though, is every time you go down a grid, you've gone down 5 meters. And every time you go over one grid, you've gone 2 seconds. So I'm going -5 meters per 2 seconds. You can leave it at that. Or if you want, you could simplify this. -2.5 meters per second. But it's important to pay attention to the scale. If this confuses you, make a star on this slide, and I'll go over it and I'll answer it with a few more examples on Thursday. Last kind of graphs that we're going to talk about today are velocity and time graphs for motion that's at a constant velocity. These graphs, you have time on the x-axis and velocity on the y-axis. If you're moving at a constant velocity, these graphs are going to look kind of like stairs, is how I would describe them, where you're going to have sections of horizontal segments. And that's because since my velocity is constant, the way we show constant on a graph is a flat line. It was at 3, then it was at 3 again, and it stayed at 3 until suddenly it changed. We will talk about things that are more real world when that change is happening over time on Thursday. But today we're going to kind of pretend like we're robots. We moved, we stopped. We turned around, we stopped. We're not going to have a lot of in-between or gradual changes over time. But these graphs, when you're looking at them, they tell you how fast is an object moving in any amount of time. So not where is it, but how fast is it. This graph, for example, I was traveling at 3 meters per second, and then I slowed down, and then I stopped. The entire time my velocity was positive, so I was moving forwards the entire time. I just slowed down and stopped. Okay, a big idea for velocity and time graphs is that if a graph ever crosses the x-axis, so it switches from positive to negative, when that cross happens, that's when you turned around. So this object was traveling forwards at 3 meters per second, slowed down, and then it turned around and went backwards, the direction it came from, at -3 meters per second. So if you cross the line on these graphs, I'll write this so it's important. If you cross the line, and by the line I mean the x-axis, you just turned around. And we're going to practice this in more than one way. This is before, like in the next 2 weeks. But this is the magic line where you turn around. Some other features of a velocity time graph is that you can look at it to find how fast you are moving. And those velocity time graphs, they're going to make a rectangle. Like we kind of looked at a graph that looked like this. We can find the area, make a graph and find the area of that shape. The area of a velocity time graph tells you how far you moved. Let's slow down, and a lot of people, this makes more sense if we try to think about it. If I'm taking an area of a rectangle, areas of rectangles are base times height. The base is it's my time in seconds. The height is my velocity in meters per second. What I'm physically doing is taking a second and multiplying by a meter per second. This is really weird the first time you do it, but usually by like day 2 or 3, students kind of like this. The seconds are going to cancel, and I'm left with just meters. We're going to try a few examples with numbers. Okay, we're going to start with easier questions and then move to some more challenging questions. You guys can do this. First, it says, look at the graph on the right and find out how fast the object is traveling at 1 second, 3 seconds, and 6 seconds. Questions like this on a velocity time graph only require you to read the graph. So at 1 second, I was at a velocity of 3 meters per second. I found the spot on the graph where 1 met the line. At 3 seconds, I have a velocity of 1 meter per second. And at 6 seconds, I have a velocity of 0 meters per second. Okay, now we're going to try to do this weird displacement thing. It's weird at first, but I know you guys can do it. At 1 second, I will have traveled at 3 meters per second for 1 second. I can take 3 meters per second and multiply by 1 second. I'm getting 3 meters. After 1 second, I have displaced 3 meters. Okay, after 3 seconds, it gets a little bit different. Let me try to erase. Oh, look at that. Okay, after 3 seconds, I need to now find, I'm going to look at this as like I have a baby square, and then I have a rectangle. I need to find the total area that the graph encloses. So after 3 seconds, I would think of this as I have a big triangle and a baby triangle. The big triangle has a base of 2 and a height of 3. The baby triangle has a base of 1 and a height of 1. 2 times 3 is 6. Sorry, that was a bad addition sign. Plus 1 times 1 is 1. 6 plus 1 is 7. Here's a cool shortcut for area. Just count the squares. 1, 2, 3, 4, 5, 6, 7. There's my area. Okay, now we're going to try for 6 seconds. Oh, it's not erasing all the way. Why is it doing that? There we go. Sorry, I don't use Explain Everything very often. Okay, at 6 seconds, right here, I want to find the area of this rectangle, the little rectangle, and the big rectangle. Well, we figured out the big rectangle is 6. The little rectangle is now 2. 6 plus 2 is 8 meters. Okay, we're going to do some bringing it together, practicing more than one concept at once for these last couple examples. You guys are doing amazing. This example, we're trying to take some data and turn it into a position graph and then a velocity graph. So it says Angela is running to catch a bus 15 meters away. We're going to use the data from the table below to create a position time graph and then answer some of the following questions. So at time 0, my position is 0. At time 1, my position is 3. So I'm just going to plot these points. You demonstrated last week on the quiz that you are great at this. At time 2, my position is 6. At time 3, my position is 9. Some of you are probably seeing a pattern. At 4, my position is 12. And at 5, my position is 15. So I made a position and time graph. This said, is she running at a constant speed? If so, what is it, and what would her velocity time graph look like? Well, as Angela runs, if I try to draw a trend line, oh, I can do this. Hang on. Consistent line width. I think I can do this. Let's see. No, that was terrible. Okay, imagine that was better. If I try to draw a trend line or look at the data, every second, Angela is 3 meters more than she was the second before. That means her speed is 3 meters per second, and it's constant. So on a graph, sometimes students try to make these graphs look really crazy. Velocity graphs are often going to be kind of boring. I'm going to go 1, 2, 3, and it's just going to stay at that speed, 3 meters per second. Velocity and time, meters per second, seconds, 1, 2, 3, and she did that the whole trip. 1, 2, 3, 4, 5, all 5 seconds. She just stayed at a constant speed. Okay, next example. Carlos places a constant motion vehicle on the ground and releases it so the vehicle travels down the hall at 5 meters per second in a straight line for 10 seconds. Draw the velocity time plot of the car's motion and determine its displacement after those 10 seconds. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's my 10 seconds time. And my velocity is 5 meters per second. 1, 2, 3, 4, 5. And it's going to keep a constant speed of 5 meters per second the entire time. To find how far I went during that time, the trick we're going to use in this class is to find the area of the graph. This graph is a single rectangle. It has a base of 10 seconds times a height of 5 meters per second. 10 times 5 is 50, and the units that I'm left with are meters. Thank you guys so much for rolling with it today. This is not the ideal way to deliver this, but it's just what it had to be. You would not want me in school today. Next class, we're going to talk about acceleration. And the thing I'm going to tell you is that it means it's a changing velocity. A lot of you have heard this before. What I would like you to do now for the next probably 10 to 15 minutes, but you're going to scan this QR code. It's also linked on Schoology. And you are going to, it'll open, I think also if you open the PDF, you can click and it will take you to that website. But it will open a motion graph matchmakers activity. Work by yourself, or if you want to move and work with a friend or two, small groups. Try to group these graphs into different categories. Again, anything that confuses you, bring questions, because we'll do this together at the beginning of class on Thursday. After you're done playing with that motion graph makers, again, probably about 10 minutes, try to look at ClassKick slides 8 through 11. I'm not going to have them due until after the long weekend, so that if you have questions, you can bring questions on Thursday and then work on them over the weekend. But ClassKick slides 8 through 11 are all covering this constant velocity. You guys are fabulous. I miss you, and I wish I was there.